Welcome to another module in this massive open online course on estimation for wireless communications. So far we have looked at maximum likelihood estimation both in the context of a sensor network and also in the context of a wireless communication system, where we have looked at maximum likelihood channel estimation for a wireless communication system. Let us now look at something analytical and something a bit more fundamental, that is we are going to talk about the Cramer-Rao lower bound. So what we are going to talk about today is known as the Cramer-Rao bound, and it's also abbreviated as CRB. And what is the Cramer-Rao bound? The Cramer-Rao bound represents a fundamental lower bound on the variance of an estimate. So, the CRB gives us a convenient way to characterize the performance of an estimator. What it gives is the best achievable performance of an estimator, that is the lowest possible variance that can be achieved by an estimator. So, it is a lower bound on the variance achievable by an estimator. So, it yields, so the Cramer-Rao bound is a lower bound on the variance of estimation, or in other words that the variance of any estimator has to be greater than this, the Cramer-Rao lower bound. So, to derive the Cramer-Rao bound, let us start with the likelihood function corresponding to the parameter h. So, remember we have already looked at the likelihood function for the unknown parameter h, and this likelihood function is denoted by P of y bar parameterized by h, where h is the unknown parameter and y bar is your observation vector or vector of observations. So, to derive this Cramer-Rao bound, which is a lower bound on the variance of any estimator, we start as usual with something that is very fundamental to the context of estimation, that is the likelihood function. And the likelihood function, as we are all very familiar with by now, it is denoted by P y bar semicolon h, where h denotes the unknown parameter and y bar denotes the vector of observations. Remember, y bar is the n dimensional vector. We have n observations, y1, y2, yn, and y bar is this vector y1, y2, yn. So, y bar is this vector. So, again just to refresh your memory, y bar is the observation vector y1, y2 up to yn. This is the observation vector y bar, which is y1, y2 up to yn. Now, also recall that this observable likelihood function P y bar h has a dual role. This is, remember the way we derived it, this is the likelihood function with respect, this is the probability density function of the observations y bar. So, this is the probability, and this is an important point, this is the probability density function, that is the PDF with respect to the observations of the observation vector y bar. So, recall that this likelihood function is nothing but the probability density function of the observations y1, y2 up to yn, that is the joint probability density functions of the function of the observations y1, y2 up to yn parameterized by the unknown parameter h. And when we view it as a function of the unknown parameter h, this is a likelihood function. Therefore, the likelihood function is also a probability density function. Hence, naturally, since the integral of the probability density function is 1, this probability density function must integrate to 1. Therefore, since this likelihood function is also a probability density function with respect to the observations, we must have integral minus infinity to infinity. It naturally follows that integral minus infinity to infinity p y bar h dy is equal to 1, dy bar is equal to 1, that is the integral of this probability density function is equal to 1. Now, differentiating this with respect to h, what we do now is we differentiate this with respect to h. Differentiate with respect to h, and therefore, what we have is dou by dou h of integral minus infinity to infinity p y bar parameterized by h dy bar equals dou by dou h. Derivative of the right hand side is derivative of 1 with respect to h, but the derivative of this constant 1 with respect to h is 0, which means the partial derivative of the quantity on the left with respect to h is 0. Now, we move this derivative operation inside. This implies basically moving this inside, what we have is integral minus infinity to infinity dou the probability density function, the partial derivative of the probability density function with respect to the unknown parameter h times dy bar is equal to 0. That is what we have. And now, observe something, I can multiply and divide by this probability density function p y bar, so parameterized by h. So, I am multiplying and dividing and now multiplying by the probability density function of y bar parameterized by h, which is equal to 0. Now, if you observe this quantity, this quantity is nothing but the partial derivative of the log likelihood function. This is dou by dou h log of the natural logarithm of the probability density function of y bar parameterized by h, because the probability density function of the log likelihood, that is the probability density, that is the derivative, partial derivative of the logarithm of p y bar parameterized by h is 1 over p y bar parameterized by h times the derivative of p y bar parameterized by h. Alright. So, this is nothing but, again just to rehash the same thing, this is nothing but basically 1 over p y bar, the derivative of the log likelihood is 1 over p y bar parameterized by h times the derivative of p y bar parameterized by h with respect to h, and that is what I have. Therefore, now I can write this implies that minus infinity to infinity the derivative of the log likelihood p y bar parameterized by h times p y bar parameterized by h dy bar equals 0, and now I can multiply by h on both sides. So, multiplying by the unknown parameter h on both sides, I have minus infinity to infinity integral minus h times integral minus infinity to infinity the derivative of the log likelihood p y bar parameterized by h times p y bar parameterized by h dy bar is h times 0, which is again 0. And now, finally, moving h inside, I remember I can move the integral h inside the integral because the integral is with respect to y bar. So, I can move h inside the integral dou by dou h, the logarithm of p y bar h times p y bar h dy bar equal to 0, and therefore, let us call this result as your result number 1. So, I am calling this as basically the result number 1. What I have is integral minus infinity to infinity h times the derivative of the log likelihood function log p y bar parameterized by h times p y bar parameterized by h dy bar is basically equal to 0. This integral on the left is equal to 0, and we have derived this property which we are subsequently going to employ in deriving the Cramer-Rao bound for the variance of estimation of the parameter. Alright. Now, let us also consider an unbiased estimator of the unknown parameter h, which means the expected value of the estimate, that is the expected value of the estimate h hat is always h. That is what we have seen in the previous modules, that is an unbiased estimator is one such that the expected value or the average value of the estimate is equal to the true value of the unknown parameter h. So, considering now an unbiased estimator, what I have is that the expected value of h hat, that is the average value of the unknown of the estimate is always equal to the true value of the underlying unknown parameter h, which means writing this in mathematical terms, this means the expected value is nothing but the expected value of the quantity is nothing but the quantity times the probability density function times dy bar, which we are saying is equal to h. What is this? This quantity here is basically expected value, the h hat multiplied by the probability density function and integrated between minus infinity to infinity. Therefore, this is nothing but expected value of h hat, or basically your average value of h hat, the average value of the unknown, average value of the estimate h hat. Now, again differentiating this with respect to h. So, what we are going to do, again we are considering an unbiased estimator, that is the expected value of h hat is equal to h, which means the integral minus infinity to infinity h hat times the probability density function p y bar parameterized by h dy bar is equal to h. Now, we differentiate on both sides with respect to h. Of course, when we differentiate on the right with respect to h, that derivative is 1, because the derivative of h with respect to h is simply 1. So, basically let us differentiate now both sides with respect to h, differentiate differentiating both sides with respect to h. What we have is basically dou by dou h, the partial with respect to h minus infinity to infinity h hat p y bar h dy bar, and differentiating now on the right, what we have is dou by dou h of h, but the derivative of h with respect to h equals 1. Therefore, to put it simply, what we have is dou by dou h, or is dou by dou h integral minus infinity to infinity h hat p y bar parameterized by h dy bar equals 1. Now, moving the derivative inside the integral, So, basically now moving dou by dou h inside the integral, what we have is basically, look at this, this is h hat times dou by dou h p y bar parameterized by h dy bar equals 1, where when we move the derivative inside the integral, we do not need to consider the derivative of h hat with respect to h, because h hat is the estimator and estimator depends only on the observations y bar. So, it does not depend on the unknown parameter h, alright. So, we are moving the derivative dou by dou h directly to p, that is the probability density function p y bar parameterized by h, and now you can see I can once again multiply and divide by p y bar. So, now multiplying and dividing by p y bar parameterized by h, I have integral minus infinity to infinity h hat 1 over, first I am dividing with respect to the probability density function dou by dou h p y bar h. Now, I am multiplying the probability density function p y bar parameterized by h dy bar equals 1. And now, if you look at once again similar to what we have done before, if you look at this quantity 1 over p y bar parameterized by h times dou by dou h of p y bar parameterized by h, this is nothing but the partial derivative of basically the log likelihood function, partial derivative of the log of the probability density function of the observations y bar parameterized by h. Therefore, this implies basically that minus infinity to infinity h hat dou by dou h log p of y bar parameterized by h times p of y bar parameterized by h dy bar is equal to 1, and let us call this as result number 2. So, what I am denoting this, so we derived two results basically. So, this is your result number 2. So, previously we have derived result number 1 and now we have derived result number 2. Now, let us subtract 1 from 2. So, let us look at these two results. We have result number 1 over here and we have result number 2 over here, and now performing result number 2 minus 1 what we have, remember what we have, let us write again for the sake of convenience. I think it would be better if we write both the results. Result number 2 is basically integral minus infinity to infinity h hat dou ln p y bar h by dou h p y bar h dy bar equals 1, and result 1 is basically that integral minus infinity to infinity h times dou ln p y bar h divided by dou h p y bar h dy bar is equal to 0, in fact is equal to 0. Now, performing 2 minus 1, now you can clearly see when I make result 2 minus result 1, that implies, clearly implies what does it imply? This implies, now if you can clearly see, this implies h hat minus h times the derivative of the log likelihood function with respect to h times the probability density function of y bar parameterized by h, or basically the likelihood function with respect to h dy bar is equal to 1, alright, and this is a central result. So, and if you look at this quantity h hat minus h, this is nothing but your estimation error, right. So, what we have here is basically h hat minus h, which is basically the estimation error. So, we have derived an interesting result for the estimation error, and now if you look at this, this is basically the estimation error, this is the derivative of the log likelihood. What is this? This is the derivative of your, this is the derivative of the log likelihood. Now, remember we are multiplying this by the probability density of the probability density function of the observation vector y bar, which means this is basically nothing but the expected value. Look at this, this is basically equal to the expected value of the error times the derivative of the log likelihood function with respect to h, and we are saying this expected value of this product is equal to 1. So, take a look at this again, and this requires some understanding and some clear thinking, alright. So, please go over this derivation again. What we have derived is, we have derived an interesting result which states that the expected value of the product of this estimation error h hat minus h times the derivative of the log likelihood function of the log likelihood function of the parameter h with respect to h is equal to 1. That is, the expected value of this product is equal to 1. And now therefore, we can now use the Cauchy-Schwarz inequality, which basically states that the expected value of x y is greater than or equal to the expected value, or the expected value of, which states that if you have two random variables, for any two random variables, x y, x comma y, it must be that the expected value, the square of the expected value of the product x y is greater than, or basically the product expected value of x square times expected value of y square must be greater than the square of the expected value of the product x y, and therefore, now we can use this interesting result. This is basically your Cauchy-Schwarz inequality for random variables. This is your the Cauchy-Schwarz inequality Cauchy-Schwarz inequality for random variables, and now therefore, we can use this Cauchy-Schwarz inequality on this product by treating this h hat minus h, by treating this random variable h hat minus h as our random variable x, by treating this derivative of the log likelihood function as our random variable y, and therefore, we have expected h hat minus h whole square times expected derivative of the log likelihood function with respect to h whole square is greater than or equal to expected value of h hat minus h square of the expected value of h hat minus h times the derivative of the log likelihood function, which is basically equal to the product. The expected value of the product is 1. So, this is basically greater than or equal to 1 square, which is equal to 1. Therefore, now we can write the expected value of h hat minus h whole square times the derivative of the log likelihood function expected value of h hat minus h whole square times expected value of the derivative of the log likelihood function whole square times the derivative of the log likelihood function, expected value of the derivative of the log likelihood function whole square is greater than or equal to 1. Therefore, now moving this quantity to the right, we have expected value of h hat minus h whole square is greater than or equal to 1 over the expected value of the square of the derivative of the log likelihood function, and this is basically, now if you can see, this on the left is basically your variance of the estimator, that is the square of the deviation, and this therefore it gives a fundamental bound on the variance. This is therefore your Cramer-Rao bound. So, it says that the variance of this estimator, so this is basically nothing but this is basically your Cramer-Rao, this is basically your So, what we have derived is we have derived this result which states that the expected value of h hat minus h square, that is basically the variance of this estimator, and that is for any particular estimator as long as it is unbiased, that is the variance of any particular estimate h hat, alright, not necessarily only the maximum likelihood estimate, but any particular estimate h hat, as long as it is unbiased, the variance is always greater than or equal to 1 over the expected value of the square of the derivative of the log likelihood function of the parameter h with respect to h, alright, and this is a fundamental bound on the variance of any estimator, and this is known as the fundamental bound on the variance of any unbiased estimator for that matter, speaking more precisely and exactly, and this fundamental bound on the variance of any unbiased estimator is known as the Cramer-Rao bound, or more explicitly the Cramer-Rao lower bound. Alright, it is automatically understood that it is the lower bound for the variance of estimation, therefore, this is also known as the Cramer-Rao lower bound or the Cramer-Rao bound, and as we already said, this is abbreviated as CRB, this is the Cramer-Rao bound. And look at this quantity, if you look at this quantity, it is interesting, if you look at this quantity in the denominator, this quantity, the expected value of the square the expected value of the square of the derivative of the log likelihood function, this is known as the Fisher information I of h, this is known as the Fisher information I of the parameter h. So, this basically this quantity is denoted by the Fisher information. The Fisher information of the parameter h. In some sense, this basically quantifies the information that the log likelihood function provides about the unknown parameter h, and therefore, the larger the Fisher information. Naturally, the lower is the estimation variance, that is basically the larger the amount of information that your log likelihood function provides with respect to h, the larger is the Fisher information, and therefore the estimation variance, because the information provided is higher, you expect the estimation variance, the variance of estimation to be lower, and that is indeed what is reflected in this Cramer-Rao lower bound, that is the variance, the minimum variance, the lower bound on the variance of estimation is basically given by the inverse of the Fisher information. So, we can also write this as basically expected value of h hat minus h whole square is greater than or equal to the inverse of the Fisher information, that is 1 over E, the derivative of the square, the average value of the square of the derivative of the log likelihood function, and this is basically your Fisher information. This is basically the result for the Cramer-Rao bound. This is basically your, let me again write this explicitly, this is again the Cramer-Rao bound for parameter estimation, or also the Cramer-Rao bound, or basically the Cramer-Rao lower bound for the estimation of the parameter h. So, what we have derived today is something very fundamental. We have considered basically an unbiased estimator, that is h hat for any unknown parameter h, and we have derived a fundamental lower bound on the variance of estimation for this parameter h, and we have demonstrated, and this we have said this fundamental bound on the variance of any unbiased estimator is given by the Cramer-Rao bound or the Cramer-Rao lower bound. We have derived an expression for this Cramer-Rao lower bound, and we have demonstrated that the estimation variance, the average value, that is the expected or average value of h hat minus h whole square is greater than or equal to 1 over the expected value of the square of 1 over the expected or average value of the square of the derivative of the log likelihood function of h with respect to h, and this basically this expected value of the square of the derivative of the log likelihood function is basically also the Fisher information of the unknown parameter h. Alright, so the Cramer-Rao lower bound yields a fundamental bound on the fundamental lower bound on the variance of any unbiased estimator h hat of any parameter h. So, we will stop this module here, and we will explore other aspects of this, and in fact other applications and examples of the Cramer-Rao lower bound in the subsequent modules. Thank you very much.